Hello everyone, welcome to our channel Mathematics Pathshala. This is a problem of CSIR NET December 2023 Mathematical Sciences. This is a problem of real analysis part C and the question ID is 704067. So let us now solve this question. See that here says that which of the following statements are true. So there are four statements given. So one by one we will analysis the options. So let us first look at option 1. The function f such that R2R defined by fx equal to box x sin 1 by x for x not equal to 0, 0 for x equal to 0. So it says that this function has a discontinuity at 0 which is removable. So if f has a discontinuity at 0 which is removable, then we must have limit x tends to 0 plus fx equal to limit x tends to 0 minus fx. Both should exist and they should be same. So for this we now calculate limit x tends to 0 plus fx equal to limit x tends to 0 plus sin 1 by x sin 1 box x sin 1 by x box x sin 1 by x equal to box x sin 1 by x. So when x tends to 0 plus box x equal to 0, so it is limit x tends to 0 plus 0 into sin 1 by x, that is equal to 0, and limit x tends to 0 minus fx, that is equal to limit x tends to 0 minus so when x tends to 0 minus box x is minus 1, so it is minus sin 1 by x, and it does not exist. So as limit x tends to 0 minus fx does not exist, so f cannot have a discontinuity at 0 which is removable. So option 1 is not the correct option. Now look at option 2. The function f from close to 0 open infinity to r defined by fx equal to this sin log x for x not equal to 0 and 0 for x equal to 0 has a discontinuity at 0 which is not removable. So for this same we have to limit x tends to 0 plus fx sin sorry, actually we now okay, no problem. Actually we should not calculate limit x tends to 0 minus because the function is defined from close 0 to open infinity. So for this function f has a discontinuity at 0 which is if f has a discontinuity at 0 which is removable, then we must have this limit x tends to 0 plus fx exist, which may be different from f of 0. So we have to calculate only this limit x tends to 0 plus fx. So this is sin log x now just as x tends to 0 plus, then log x is negative, so we can write this like this, one minus here, and as sin minus x equal to minus sin x, using that we can write this sin minus log x. Now as x tends to 0 plus, this minus log x is positive. So now let us put just minus log x equal to say y. Then we have as x tends to 0 plus, as x tends to 0 plus log x tends to minus infinity, so minus log x tends to infinity plus infinity. So now putting this in the limit, we have limit minus is here, limit y tends to infinity sin y. So now this is minus limit y tends to infinity sin y, and we know that this does not exist. This does not exist. So if f has a discontinuity at 0 which is removable, then we must have this limit x tends to 0 plus fx exist. So as it does not exist, so the discontinuity of f at 0 is not removable. So option 2 is the correct option. Now look at option 3. The function f such that R2 are defined by this has a jump discontinuity at 0. So for this we have to again calculate limit x tends to 0 minus fx. This is limit x tends to 0 minus e to the power 1 by x, and clearly this actually does not exist, or we can say this is actually better to say as x tends to 0 minus, then this 1 by x tends to minus infinity, and e to the power 1 by x tends to also sorry mm, as x tends to 0 plus sorry as x tends to 0 minus, then this 1 by x tends to minus infinity, right? So this e to the power, just if we just put here some change the variable. So suppose we put here 1 by x equal to say y, then as x tends to 0 minus, we have y tends to minus infinity. So then the limit becomes limit y tends to minus infinity, this e to the power y. So this limit is as y tends to minus infinity, then e to the power y tends to 0. So first we thought that this limit does not exist, so that is not the case. This limit actually tends to 0. Okay, now let us calculate limit x tends to 0 plus fx, that is limit x tends to 0 plus e to the power 1 by x plus 1. So as x tends to 0 plus, this is 1 by 0 plus 1, that is e only. So now see, also we have f of 0 equal to e to the power 1 by 0 plus 1, that is e. So here when x tends to 0 minus, this is 0, and when x tends to 0 plus or x equal to 0, it is e. So if we try to draw the picture of this curve, only the neighborhood of 0, so it becomes like that. As x tends to 0 minus, it is just 0, and when it is tends to 0 plus, so here 1, suppose here 2, suppose here 3, so suppose here it is e. So this is the case. So when this x tends to 0 plus, the value is here. Is so so clearly this function has a jump discontinuity at 0, because when it comes to 0 from left side, it is 0, and at 0 it jumps to e, and also x tends to 0 plus, this is e. So clearly this function has a jump discontinuity at x equal to 0. So option 3 is the correct option. Now look at option 4. Fg such that 0, 1 to r be two functions of bounded variation, then the product Fg has at most countably many discontinuities. We have a result that if f is a function of bounded variation, then the set of all discontinuities of f is a countable set. So if we suppose that A is the set where such that f is discontinuous at all the points of A, so x belongs to 0, 1 such that f is discontinuous at x. So all such x in 0, 1 where f is discontinuous. So now by that result, this A is a countable set. And if we suppose that B is that set such that all such x belongs to 0, 1 where such that G is discontinuous at x, then also by that result B is countable. And clearly if we take one point which does not belong to A as well does not belong to B, then that point f is continuous, g is continuous, and so fg will be continuous. So clearly fg is continuous in this A union B complement. So fg, so the if we consider the set S such that where fg is discontinuous, so x belongs to 0, 1 such that fg is discontinuous at x, so clearly this set should be subset of A union B, because if we take one point which belongs to complement of this A union B, then at that point Fg is continuous. So the set of discontinuities of Fg is a subset of A union B. So here A is countable, B is countable, so A union B is countable, and as S is a subset of this, so S is countable. So the set of discontinuities of Fg is at most a countable set. So Fg has at most countably many discontinuities. So option 4 is the correct option. So here look at the options again. So here option 1 is not the correct option, and option 2, 3, 4 are the correct options. So this is the solution of this problem. Thanks for watching.